Now we move on to combining all of the elements that we've learned so far, resistors, inductors, and capacitors, into series and parallel circuits, and understand how we handle the reactance then given sinusoidal sources and something called resonance, when we have the inductors and the capacitors working in harmony with each other based on the frequency, giving what we call a frequency response to that of those circuit elements. So we're going to look at them individually, series again, parallel, series parallel, and then the last section talks about some special topics. So we've got some new terms here to deal with. You've probably seen them before, where we talk about the resonance, the resonant frequency, what's a tank circuit. We've already talked a little bit about filters and how the inductor and capacitor becomes the key elements in a filter circuit. The half power frequency, power transfer of energy to the load, and then something called selectivity. So the first section then that we're going to look at then is, again, the series circuit. So we're just going to step our way through it. So in a series RLC circuit, it contains a resistor, an inductor, and a capacitor, or multiple elements. Since the inductive reactance and capacitive reactance have opposite effects on the circuit phase angle, the total reactance then is less than either individual reactance. So we will look at how these build as we move through these circuit types and parameters. So our simple series RLC circuit will look something like this. And again, let's start off simply. In this case, we're going to look at it at a simple series RL circuit where we have the elements again given to us in its natural units, inductors in henries, capacitors in farads. So we need to go through it step by step like we've done before and put everything into the reactive components or terms. So everything needs to be in ohms. So we're given a source at a frequency of 100 kHz. So that will be the frequency of interest for the inductor and the capacitor. So the first thing that we need to do then is convert our capacitor and inductor into its reactive terms. So 1 over 2 pi FC then gives us 3.39 k ohms for the capacitive reactance. 2 pi FL gives us 6.28 k ohms for the inductive reactance. So now we start treating those values phasorially or vectorially, however you want to think about it. Each is correct, but we call it phasors in electronics, as we've said before. So the total value of the reactance for those two components, the inductor and the capacitor, then becomes the absolute value of the difference in the two, X sub L minus X sub C. So 6.28 k ohms minus 3.39 k ohms gives us a value 2.89 k ohms, and we identify it now as the combination of those two. As we said before, it'll be less, but in this case it is a more inductive circuit. So the dominant component in this case is the inductor. So to calculate the total impedance then, we put everything together using our J terms. So we have R, the resistance value, plus that difference, JX sub L minus JX sub C, and we end up with 5.6 k ohms plus 2.89 k ohms for this circuit. The next step then is converting this rectangular relationship into a polar relationship. So there's our value that we've learned before. So we've got the Pythagorean theorem, the vector sum of the two, and then the angle that it would in fact form. It's missing, I see here we're missing a term, the inverse tangent. So there should be an inverse tangent right there. So when we do this, we end up with the vector sum here, which gives us 6.3. And when we take the inverse tangent of the ratio of x sub x total to r, we get 27.3 k ohms. So remember to put the inverse tangent term in there. I apologize. You'll recall that a capacitive reactance varies inversely with frequency and that the inductive reactance varies directly with frequency. Again, this is a matter of one is a quotient, one is a product. The um, capacitor is an inverse because it's a quotient. The inductive is a product because it's a product of all of the terms in the numerator. So the combined effects of the reactances then as a function of frequency, as we've seen before, you can see that in the case of the capacitive reactance, we're in this negative moving angle. In the inductive reactance, we have this positive moving angle as we increase the frequency. So when we start to look at the relationship of x sub c to x sub l, we have a point in here that we're going to be concerned with, which is called the series resonance. So on this half of the graph for the frequency and the resonance, we have capacitive. X sub c is larger than x sub l. On this half of the graph, more inductive, x sub l is greater than x sub c. So you can see we have a linear relationship for x sub l and a nonlinear relationship for x sub c. And the point where they cross, then x sub l equals x sub c, and it becomes known as the series resonant points. So let's take a look at an example here, and then we'll stop on this one. For the following input frequency, find the impedance in polar form for the circuit. Note the change in magnitude and the phase angle with the frequency. So we're given our values then in henries and farads, so we're going to have to convert those, and at a frequency of 1 kHz we will calculate those values. So x sub c at 1 kHz gives us 7.23 k ohms. X sub l at 1 kHz gives us a value of 628 k ohms. So the circuit is clearly capacitive, and impedance then is the calculation as we've seen before. We take the difference in x sub l and x sub c. There's our inverse tangent, x total over r. So if we take the difference in x sub l, x sub c, the absolute value, we get a value of 6.60 k ohms. Okay, so that value then becomes our term here. 303 k ohms that should be 3.3 k ohms. So that should be a decimal point there, not a zero. And the inverse tangent of the relationship 6.6 k, 3.3 k, the k's cancel out, and we end up then with a total impedance then of 7.38 at an angle of minus 63.4 degrees in k ohms. So in the next step, we move it up to 2 k ohms. You can see your values start changing. Circuit is still capacitive and the impedance given. So now we have a value when we go through it. Go ahead, again, pull out your calculators, work through these examples, make sure you understand them. We have a total impedance of 4.06 k ohms at an angle of minus 35.6. We increase it to 3.5 k. The circuit then is very close to being purely resistive because x sub c and x sub l are nearly equal. So we're approaching that resonance, but it's still slightly capacitive. So again, we do the calculations. Now we end up with 3.3 k ohms at an angle of minus 2.26. At 5 kHz, now the circuit is predominantly inductive, and the impedance becomes 3.71 k ohms at an angle of 27.1 degrees. Okay, so you can see here we've moved from our negative angles in each of these steps: minus 63, minus 35, minus 2.6. We're getting closer and closer, and now we jump to it being a predominantly inductive circuit when we move as a positive angle. So when we come back, we'll continue our analysis.